Hi, thanks so much for checking my poster video. I'm Polina and I'll be talking about essential considerations for exploring visual working memory storage in the human brain. Visual working memory is commonly assumed to rely on a distributed network of brain regions. However, the role of individual cortical areas, such as early visual cortex and intraparietal sulcus, remains highly debated at the moment. In this work, we argue that an important factor affecting both results and their interpretations is a choice of analysis approach. We reanalyzed two datasets and demonstrate how analysis choices influence the results and consequently might lead to diverging interpretations about the role of different brain areas in visual working memory functioning. The first question which we investigated is whether working memory representations are resilient towards distraction. We used the dataset from the study by Rademacher and colleagues, where participants were doing one retrocue task. They had to memorize an oriented grading, and after a delay interval, they were doing a continuous report task, adjusting a bar to the memorized orientation. Importantly, during the delay, participants saw various types of distraction. In this analysis, we combined smaller regions of interest for a better assessment of distraction effects per cortical area, and we used two different but widely employed analysis approaches. We trained the model on an independent sensory data and on the memory delay data using leaf-one-out cross-validation. Here you see the plot after we trained the model on the memory delay data. The smaller inserts reflect behavioral performance. This training approach revealed mnemonic information in early visual cortex and intraparietal sulcus, where both EVC and APS show resilience against distraction, and EVC also tracks changes in behavioral recall across two experiments. However, when training the model on the sensory-driven responses, we found mnemonic representations in EVC but not in APS, and representations in EVC were reduced with distraction in the absence of behavioral deficit. Overall, we show here that the results depend on the analysis approach, and the approach, in turn, depends on how one defines visual working memory, either as including any representation pertaining the delay period activity, or restricting the definition only to representations that generalize from sensory-driven responses. Neither analysis approach is inherently better, of course, and each approach depends on the research question. The second question we wanted to answer is whether representation of unattended memory item, or UMI, can be decoded from early visual cortex. Here we used a data set from the study by Christoffel and colleagues. There, participants were doing double retrocueing task. They had to memorize two items, and the subsequent cue could select any of them as relevant for the upcoming comparison task. Then the second cue could also pick any of the memorized items for the second comparison task. In this way, throughout the trial, participants had to remember both items, but after the first cue, one of these memory items was more prioritized than the other, and we refer to this one as attended memory item, or AMI, whereas the other item in memory was left less prioritized but not forgotten, and we call it unattended memory item. The previous analysis was performed within conditions, that is, to look for UMI, the model was trained on the item condition itself, but this approach might not have been powerful enough for detecting UMI representation in early visual cortex. This time we trained the model on the AMI to decode UMI. Training on stronger mnemonic representation of AMI indeed helps to uncover weaker mnemonic representation of the UMI, both in EVC and IPS. And again, when training the model on signals evoked by the UMI themselves, such items could only be detected in IPS. This result showcases how a previous null finding in fact depends on analysis choice, and it demonstrates how one should never prematurely interpret null results as evidence of absence. Another question, which we explored in both data sets now, is whether representations in EVC and IPS relate with the behavioral performance. Importantly, the reanalysis of Rademacher dataset is performed across trials but within participants, and the reanalysis of Christoffel dataset is done across subjects. And across both levels of analysis, we found a relation between representations in EVC and behavioral performance, but not between IPS and behavioral performance, as you might see from the plots. Since these are the two independent levels of analysis, which could potentially be affected by different factors, and more on this you can read in our recent publication, we argue that evaluating results across multiple levels can only strengthen our understanding of the brain-behavior relationship. So to wrap up, our reanalysis shows that both EVC and IPS are involved in visual working memory storage, but in different ways, possibly storing mnemonic contents in different formats. Thus, analysis choices which may tap into different aspects of visual working memory can differentially affect the results. Therefore, rather than questioning the role of individual areas for visual working memory storage, we should probably ask under what circumstances, or in other words, when and how is an area of particular importance to visual working memory storage. Thank you so much for your attention. Please check out our paper and hope to see you at the VSS 2021.